Okay, so today we're going to talk about alternating series and the alternating series test. So first, let me clarify what is an alternating series. It's going to be a series which has terms that alternate in sign. So general kind of structure would be something like the sum from 1 to infinity of -1 to the n times these b sub n's, which are all going to be positive. Now, the -1 to the n is going to be controlling the sign of the terms, and so if we can write it in this structure, we know we have an alternating series. Now, since n starts at 1 and we have -1 to the n, this series is going to be starting with a negative term. If we wanted the alternating series, which is starting with a positive term, we would just have this structure where we have the sum n from 1 to infinity, -1 to the n plus 1 this time, but then again times these b sub n's. All of the b sub n's we're specifying are going to be positive because if they could be positive and negative, then we might not necessarily have a series which is strictly alternating. So keep in mind, in alternating series, we want that very precise pattern of negative, positive, or positive, negative, positive, negative. All right, so the alternating series test says that an alternating series is convergent provided that 0 is less than b sub n plus 1 is less than b sub n for all n greater than or equal to 1. Well, this is basically just saying that our b sub n's are decreasing. So we have b sub n's are decreasing. And our second condition is that the limit as n goes to infinity of these b sub n's is equal to 0. So not only are the b sub n's decreasing, but they're decreasing specifically to 0. So if we have that if we have an alternating series, and we have 1 and 2 are true, then we can conclude that the alternating series is convergent. If 1 or 2 are not true, we're not going to conclude that the alternating series is divergent. It still might be convergent or divergent. We're just going to say that the alternating series test is inconclusive in that case. All right, so we're going to kind of discuss why this is true. I was originally going to prove it, but we're just going to kind of discuss it and kind of have like this will be basically like the skeleton of the proof, but I'm not going to put all of the nitty-gritty details down. So let's assume I'm looking at an alternating series like this one. So I have the sum from 1 to infinity, -1 to the n plus 1 times b sub n's. So I'm alternating in sign, and I'm starting off with a positive term. Now, my first term is going to be b sub 1. Now, if I consider my sequence of partial sums, S1 is my first term, B sub 1. And let's just suppose, like if this were a number line, let's just suppose that my S1 lands here. Now to get to S2, my second partial sum, I'm going to subtract a B2, and it's going to send me over here to S2. And then, since I have an alternating series, I'm going to add my B sub 3. Well, I know that my b sub 3 is going to be less than my b sub 2 because I know the b sub n's are decreasing, which tells me that I know that my s sub 3 is going to land to the left of s sub 1. So to get from my S3, I'm going to subtract B4. And basically this pattern is going to continue. I'll go to S5, and then I'll go to S6, and then I'll go to S7, and then S8, and I'm going to keep bouncing back and forth, right? Well, just visualizing this picture, we can list down a couple things. So first of all, if I consider the sequence of partial sums, just the even partial sums, so I'm going to call that S sub 2k, from k equals 1 to infinity. This sequence, we can see that it is both monotone increasing, and we can also see that it's bounded. And you might say, well, how do we know that it's bounded? Well, let's just look at this picture, right? The lowest my partial sums are ever going to go is this s sub 2, and the highest is this s sub 1. Now, you might ask, well, what if this exponent was that -1 to the n? well, then those would just switch. Basically, we would just reflect this image over this line, and we'd have the image for the other one. So, since the sequence is monotone and bounded, we have that it's convergent by the monotone convergence theorem. Similarly, we can look and see that S sub 2k plus 1, so those are the odd partial sums from k equals 0 to infinity, is also convergent by the monotone convergence theorem. All right, well, we know that these S sub 1, S sub 3, S sub 5, the odd partial sums, they're going to converge somewhere over here. And we know that the even ones are also going to converge somewhere over here. And so the last thing that we need to kind of sort out is, how do we know that they converge at the same thing? So that I can say that this sum must converge because the sequence of partial sums in general, not just the odd or the even, that they both converge. Well, I would be looking at limit as n goes to infinity. Oops. If I look at limit as k goes to infinity of S sub 2k plus 1, which we know exists since S sub 2k plus 1 is convergent, we can rewrite this as limit k goes to infinity of S sub 2k plus our B sub 2k plus 1, right? That's how we're going to get from S sub 2k plus 1 to S sub 2k. So we're going to add our next B sub n. Well, if I evaluate this limit, I've got limit as k goes to infinity, S sub 2k, which I know exists, plus limit as k goes to infinity of B sub 2k plus 1. Well, remember that one of the conditions for the alternating series test is that the limit as n goes to infinity of B sub n goes to 0. So then limit as k goes to infinity of B sub 2k plus 1, this is going to go to 0. And so we have that the limit of as k goes to infinity of S sub 2k plus 1 is equal to the limit as k goes to infinity of S sub 2k. And let's just call both of those S. Well, that's exactly what the series is going to converge to, is S. All right, let's do an example. It says, show that the alternating harmonic series is a convergent series. Well, I know the harmonic series is the sum n equals 1 to infinity of 1 over n. The alternating harmonic series is going to be the sum from n equals 1 to infinity of negative 1 to the n over n. Now, we have that this is an alternating series. We have two conditions to check. The first thing is we need to check that our B sub n's are decreasing. Well, the way that we can check that is we look at B sub n plus 1, which, by the way, in case it's not clear, our B sub n's are going to be 1 over n, right? So this is my negative 1 to the n. My B sub n's are going to be these 1 over n's. So B sub n plus 1 is 1 over n plus 1. And if I look at B sub n, that's just 1 over n, well, I can confidently say that B sub n plus 1 is going to be less than my B sub n for n greater than or equal to 1, for sure. So we have that the B sub n's are decreasing. The second thing that I need to check is that the B sub n's are decreasing to 0, i.e. limit as n goes to infinity of B sub n is equal to 0. So I check that. Limit n goes to infinity of 1 over n. This is in fact 0. So we can say that the series is convergent by the alternating series test, which we can abbreviate AST for alternating series test. All right, so let's talk about conditional and absolute convergence. So we've had before that a series is convergent or a series is divergent. Well, we're going to break convergence up into two different types of convergence. So we have absolutely convergent, which means not only does the series converge, but if I take the absolute value of all of the terms and I add those up, that series even converges. So essentially the series converges regardless of the sign of the terms that I'm adding up, right? The series is conditionally convergent if the original series that I'm looking at is convergent, but when I disregard all of the signs and I take the absolute value of each term, that series ends up being divergent. So it does depend on the sign of the terms. If I have a series which has positive and negative terms, I need those positive and negative terms for the series to converge. And then if the series, the original series is divergent, we just label it as divergent. We don't have conditional or absolute divergence. It is just divergent. All right, so if we know that a series is absolutely convergent, we know that the series is convergent. Now that might kind of sound a little silly, but we're going to go ahead and prove it. So we have prove that the series A sub n is convergent if the series for the absolute value of A sub n is convergent. So let's start by assuming the series with the absolute value A sub n is convergent. Okay, now what I want to show is that the series for regular A sub n is convergent. So I'm going to set up a little inequality. So if I take A sub n and I add absolute value A sub n to it, either I have a negative A sub n, and when I add absolute value of A sub n, that's going to give me 0, or I'm just going to get twice the absolute value of A sub n if A sub n was already positive. So I know that this thing is bounded between 0 and 2 times the absolute value of A sub n. Well, by direct comparison test, we know that the sum of A sub n plus the absolute value of A sub n must be convergent. Since we are given that the series of A sub n is convergent. Now, I can just multiply this by a 2, and since I have a convergent series, this is just the sum of 2 times the absolute value of A sub n. And so for sure, when I add up, when I evaluate this sum, this guy is going to be convergent. So we know this, when I take the series, is going to be convergent as well. All right, so let's try to get out that then the series for A sub n, just plain old A sub n, must be convergent. Well, I can rewrite this as the series of A sub n plus absolute value A sub n minus the absolute value of A sub n, which is equal to the sum of A sub n plus absolute value A sub n minus the sum of the absolute value of A sub n. I can break this apart because I know that this guy is convergent because we were given it, and this guy is convergent. We showed it by direct comparison test. And if I have that this is convergent and this is convergent, then I have a finite number minus a finite number. And so we actually just showed that the series for A sub n must be equal to a finite number. So this must converge. All right, let's just organize these ideas for a second. So I have the series A sub n. Now, two things might happen. First thing, maybe A sub n diverges. And then we just say the series for A sub n diverges. Maybe the series for a sub n converges. And then we have two different things that could happen if the series for a sub n converges. Either I can also check the series for the absolute value of a sub n, and this guy also converges, which means that our series is absolutely convergent. Or maybe when I look at the absolute value of a sub n and I take the sum, those diverge, or the series diverges, and that's when we call this conditionally convergent. Okay, so just a little flow chart of what we're talking about right now. All right, so I'm going to go through some true or false. I would recommend that you pause it, read it, decide what you think, and then play it to hear the explanation. So true or false, there are no geometric series which are conditionally convergent. This would be true. So a geometric series is either going to be conditionally convergent or absolutely convergent. The reason being, if this guy is convergent, it's dependent on the absolute value of r. Right? So if r is positive or negative, it doesn't really matter because we consider the absolute value of r and we check if this thing is less than 1. So if I consider absolute value of a times r to the n, this is just going to be equal to absolute value of a times absolute value of r to the n. And regardless, if r in the absolute value is less than 1 or the absolute value of r is less than 1, those two things are asking the same thing. So there are no geometric series which are conditionally convergent. They are all either absolutely convergent or divergent. Next, there are no p-series which are conditionally convergent. This one is false. We just showed that the series -1 to the n over n is convergent. But if I take the absolute value of the terms, I get the regular harmonic series, and that guy is divergent. So that tells me that the series -1 to the n over n is conditionally convergent. All right, a series with all positive terms can be conditionally convergent. This one is false. If I have that a series has all positive terms, then that means that when I take the absolute value of all of the terms, that it's just equal to the original series. Well, if the original series is convergent, so if I know that this series is convergent and it's equal to this guy, then I know that the series of the absolute value of the terms is convergent, which means that the original series would be absolutely convergent. And if the original series was divergent, then we would just label it as divergent. So we don't have conditionally convergent for a series with all positive terms. Notice that any time that we used integral test or direct comparison test or limit comparison test, we were doing those with series with all positive terms, which means we actually had that they were absolutely convergent that whole time. All right, so now there are a couple of examples here. I would recommend you pause the video, try them, and then you can look at the solutions. Okay, so for this first one, we have the series n from 1 to infinity, -1 to the n times n over n plus 1, and we're trying to determine if it's absolutely convergent, conditionally convergent, or divergent. Well, we see that we have an alternating series. Maybe our first intuition is to try the alternating series test. So we might take a note that our b sub n's are going to be n over n plus 1. And so we might check, are b sub n's decreasing? Is the limit as n goes to infinity of b sub n equal to 0? And you might notice that if we check limit as n goes to infinity of our b sub n's, that we get 1, which means that the alternating series test is inconclusive. But this is actually a really nice result to have because we can basically immediately use another test, and it's the test for divergence. So if I have that this limit is equal to 1, then when I add in this negative 1 to the n, it's not going to make this become 0, right? This limit, when I multiply in this negative 1 to the n, is still going to be non-zero. It's going to actually be bouncing back and forth between things that are close to positive 1 and things that are close to negative 1. And so, by the test for divergence, this series is divergent since the limit as n goes to infinity of negative 1 to the n times n over n plus 1 is not equal to 0. It, in fact, does not exist. All right, so that one's divergent. Now we have this next one, series n equals 1 to infinity, cosine pi times n over n plus 5. Okay, so we've got this guy. Now, you might be a little bit confused by the cosine of times n in the numerator at first, but let's just kind of plug in a couple n's and see what happens. So I'd have cosine of pi gives me a 1. Cosine of 2 pi, cosine of pi gives me a negative 1. Cosine of 2 pi gives me a 1. Cosine of 3 pi gives me a negative 1. Cosine of 4 pi gives me a 1. And you might notice that cosine of pi times n is actually just the same thing as having a negative 1 to the n. So I have an alternating series here. It's just kind of disguised. But since I can rewrite it in this form, negative 1 to the n over n plus 5, we're good to go in saying that this is an alternating series. All right, so we can use the alternating series test with b sub n's equal to 1 over n plus 5. Now, b sub n plus 1 is going to be equal to 1 over n plus 1 plus 5, which is 1 over n plus 6, which we can confidently say is going to be less than 1 over n plus 5, which is our b sub n. So we have that our b sub n's are decreasing. We can check the limit as n goes to infinity of our b sub n's, 1 over n plus 5, and that limit is very clearly equal to 0. So by the alternating series test, we can conclude that the series is convergent. Now, we're not done yet because the question was to determine if it was conditionally convergent or absolutely convergent once we get convergence. So we need to check when we take the absolute value of these terms, what happens? Well, when I take the absolute value of the terms, basically that negative 1 to the n just becomes a positive 1. So I'm going to be looking at the series n equals 1 to infinity of 1 over n plus 5 and trying to determine if this one converges or diverges, right? And just to really emphasize, all that I'm doing is looking at the absolute value of our original terms. Okay, well, if I look at 1 over n plus 5, this looks like the series with 1 over n, so I need to decide, am I using direct comparison test or limit comparison test to get out that this is probably divergent? I think the easiest one would probably be limit comparison test. So limit as n goes to infinity, 1 over n plus 5 over 1 over n. This is going to give us limits as n goes to infinity of n over n plus 5, which is equal to 1. So we can say, since series 1 over n is divergent, it's a p-series, p equals 1. By limit comparison test, the series for 1 over n plus 5 must also be divergent. Well, since we have that the original series is convergent, and when I take the absolute value of the terms, that new series ends up being divergent, we have that our series is going to end up being conditionally convergent. All right, third example, we've got the sum n equals 1 to infinity, negative 1 to the n times 3 to the n over n factorial. So we've got this guy. Okay, so we could jump right into trying to do alternating series test, and maybe we will get out that the series is convergent. But we would be doing a limit with this factorial in the denominator, which feels a little uncomfortable. Why don't we just see if we can show that the series of the absolute value of the terms, so 3 to the n over n factorial, why don't we just check if this is convergent? Because if we have that, when I take the absolute value of the terms, that series is convergent, I automatically get that the original series is convergent as well. So I'm directly trying to show that it's absolutely convergent instead of kind of doing both of the series. So I'm jumping to this one. Well, we've done something like this before. So just to remind everybody, these terms here look like, so the 3 to the n over n factorial, these look like 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4, all the way up to 3 over n. And in fact, last time we did this, we also needed this 3 over n minus 1. So the idea is that 3 to the n over n factorial is always going to be less than or equal to, if I have 9 halves, I'm just multiplying these first couple terms together. 9 halves times 9 over n squared minus n. So I'm cutting out all of these middle terms and saying, well, they're all less than 1, right? So all of these extra factors are pulling what would have just been this guy smaller, right? So I have this inequality. And also keep in mind that this is always going to be greater than or equal to 0. So we can apply direct comparison test here. Well, I want to show that this guy is convergent when I take the series. So I can use limit comparison test. So let's look at limits as n goes to infinity of 9 halves times 9 over n squared minus n over, I can compare to the series 1 over n squared, which I know is going to be convergent. I get this is equal to limits n goes to infinity of 9/2 times 9n squared over n squared minus n. And this limit's going to be 81/2, which is a non-zero finite number. So whatever happens to 1 over n squared when I look at the series is going to happen to this guy when I take the series. So just to kind of summarize, we have, since 1 over n squared is a convergent p-series, so I have it's convergent p-series. I'm going to list that p is equal to 2. Limit comparison test concludes that the series 9/2 times 9 over n squared minus n is convergent. And so, direct comparison test concludes that the series 3 to the n over n factorial is convergent. Well, we just showed that this series is absolutely convergent.